My attitude as a scientist is I don't believe any of our theories. I take them very, very seriously. I study them. I look at their implications, but none of them are the gospel. They're just the latest ideas that we have. And so the reason I study evolutionary game theory is because that's the best tool we have right now in this area. There is nothing else that competes. And so as a scientist, it's my responsibility to take the best tools and see what they mean. And the same thing the physicists are doing. They're taking the best tools and looking at what they entail. But I think that science now has enough experience to realize that we should not believe our theories in the sense that we've now arrived. In 1890, it was a lot of physicists thought we'd arrived. They were discouraging bright young students from going into physics because it was all done. And that's precisely the wrong attitude.
Yep.
Forever. It's the wrong attitude forever. The attitude we should have is a century from now, they'll be looking at us and laughing at what we didn't know. And we just have to assume that that's going to be the case. Just know that everything that we think is so brilliant right now, our final theory, a century from now, they'll look at us like we look at the physicists of 1890 and go, how could they have been so dumb?
Yeah.
So I don't want to make that mistake. So I'm not doctrinaire about any of our current scientific theories. I am doctrinaire about this. We should use the best tools we have right now.
Mm-hmm.
That's what we've got.
With humility. Well, so let me ask you about game theory. There's, I love game theory, evolutionary game theory, but I'm always suspicious of it, like economics. When you construct models, it's too easy to construct things that oversimplify just because our human brains enjoy the simplification of constructing a few variables that somehow represent organisms or represent people and running a simulation that then allows you to build up intuition. And then it feels really good because you can get some really deep and surprising intuitions. But how do you know your models aren't, the assumptions underlying your models aren't some fundamentally flawed, and because of that, your conclusions are fundamentally flawed? So I guess
Yes.
My question is, what are the limits in your use of game theory, evolutionary game theory, your experience with it? What are the limits of game theory?
So I've gotten some pushback from professional colleagues and friends who have tried to rerun simulations and the idea that we don't see the truth is not comfortable. And so many of my colleagues are very interested in trying to show that we're wrong. Mm-hmm. And so the idea would be to say that somehow we did something, as you're suggesting, maybe something special that wasn't completely general. We got some little special part of the whole search space in evolutionary game theory in which this happens to be true, but more generally, organisms would evolve to see the truth. So the best pushback we've gotten is from a team at Yale, and they suggested that if you use thousands of payoff functions, so we in our simulations we just use a couple, mm-hmm. one or two, because it was our first simulations, right? So that would be a limit. We had one or two payoff functions. We showed the result in those, at least for the genetic algorithms. And they said if you have 20,000 of them, then we can find these conditions in which truth-seeing organisms would be the ones that evolved and survived. And so we looked at their simulations, and it certainly is the case that you can find special cases in which truth can evolve. So when I say it's probability zero, it doesn't mean it can't happen. It can happen. In fact, it could happen infinitely often. It's just probability zero. So probability zero things can happen infinitely often.
When you say probability zero, you mean probability close to zero?
To be very, very precise. So for example, if I have a unit square on the plane, and I use a measure in which on a probability measure in which the area of a region is this probability. Mm-hmm. Then if I draw a curve in that unit square, it has measure precisely zero, precisely, not approximately, precisely zero. Mm-hmm. And yet it has infinitely many points. So there's an object that for that probability measure has probability zero, and yet there's infinitely many points in it. So that's what I mean when I say that the things that are probability zero can happen infinitely often in principle.
Yeah, but infinity, as far as and I look outside often, I walk around and I look at people. I have never seen infinity in real life.
That's an interesting issue.
I've been looking. I don't notice it. Infinitely small or the infinitely big. And so the tools of mathematics, you could sort of apply the same kind of criticism that it is a very convenient interface into our reality.
That's a big debate in mathematics: the intuitionists versus the ones who take, for example, the real numbers as real. And that's a fun discussion. Nicholas Geeson, a physicist, has really interesting work recently on how if you go with intuitionist mathematics, you could effectively quantize Newton, and you find that Newtonian theory and quantum theory aren't that different once you go with
It's funny.
It's really quite interesting. So the issue you raise is a very, very deep one, and one that I think we should take quite seriously, which is, how should we think about the reality of Cantor's hierarchy, Aleph 1, Aleph 2, and all these different infinities versus just a more algorithmic approach, right? So where everything's computable in some sense, and everything's finite, as big as you want, but nevertheless finite.
So yeah, they ultimately boils down to whether the world is discrete or continuous in some general sense. And again, we can't really know, but there's just a mind-breaking thought, just common sense reasoning that something can happen and is yet probability of it happening is 0%. That doesn't compute for common sense computer.
Right. This is where you have to be a sharp mathematician to really, and I'm not.
Sharp is one word. What I'm saying is common sense computer is, I mean that in a very kind of, in a positive sense, because we've been talking about perception systems and interfaces. If we are to reason about the world, we have to use the best interfaces we got. And I'm not exactly sure that game theory is the best interface we got for this.
Oh, right.
And application of mathematics, tricks and tools of mathematics to game theory is the best we got when we are thinking about the nature of reality and fitness functions and evolution, period.
Right. Well, that's a fair rejoinder, and I think that that was the tool that we used. And if someone says, here's a better mathematical tool and here's why, this mathematical tool better captures the essence of Darwin's idea. John Maynard Smith didn't quite get it with evolutionary game theory. There's this thing. Now, there are tools like evolutionary graph theory, which generalize evolutionary game theory. And then there's quantum game theory. So you can use quantum tools like entanglement, for example, as a resource in games that change the very nature of the solutions, of the optimal solutions of the game theoretic.
Well, the work from Yale is really interesting. It's a really interesting challenge of that kind of these ideas where, okay, if you have a very large number of fitness functions, or let's say you have a nearly infinite number of fitness functions or a growing number of fitness functions, what kind of interesting things start to emerging if you are to be an organism. If to be an organism that adapts means having to deal with an ensemble of fitness functions.
Right. And so we've actually redone some of our own work based on theirs. And this is the back and forth that we expect in science, right? And what we found was that in their simulations, they were assuming that you couldn't carve the world up into objects. And so we said, well, let's relax that assumption. Allow organisms to create data structures that we might call objects. And an object would be you would do hierarchical clustering of your fitness payoff functions. The ones that have similar shapes. If you have 20,000 of them, maybe these 50 are all very, very similar. So I can take all the perception, action, fitness stuff and make that into a data structure, and we'll call that a unit or an object. And as soon as we did that, then all of their results went away. It turned out they were the special case, and that the organisms that were allowed to only see that were shaped to see only fitness payoffs were the ones that were. So the idea is that objects then, what are objects from an evolutionary point of view? This ball We thought that when I saw a bottle, it was because I was seeing a true object that existed, whether or not it was perceived. Evolutionary theory suggests a different interpretation. I'm seeing a data structure that is encoding a convenient way of looking at various fitness payoffs. I can use this for drinking.
Mhm.
I could use it as a weapon, not a very good one. I could beat someone over the head with it.
Yeah.
If my goal is mating, this is pointless.
Mhm.
So I'm seeing for what I'm coding here is all sorts of actions and the payoffs that I could get. When I pick up an apple, now I'm getting a different set of actions and payoffs. For when I pick up a rock, I'm getting, so for every object, what I'm getting is a different set of payoff functions, and act with various actions. And so once you allow that, then what you find is once again that truth goes extinct, and the organisms that just get an interface are the ones that win.
But the question, just sneaking up on this, is fascinating. From where do fitness functions originate? What gives birth to the fitness functions? So, if there's a giant black box that just keeps giving you fitness functions, what are we trying to optimize? You said that water has different uses than an apple. So there's these objects. What are we trying to optimize? And why is not reality a really good generator of fitness functions?
So each theory makes its own assumptions and says, grant me this, and I'll explain that. So evolutionary game theory says, grant me fitness payoffs, right? And grant me strategies with payoffs. And I can write down a matrix for this strategy interacts with that strategy. These are the payoffs that come up. If you grant me that, then I can start to explain a lot of things. Now, you can ask for a deeper question, like, okay, so how does physics evolve biology, and where do these fitness payoffs come from, right? Now, that would be that's a completely different enterprise. And of course, evolutionary game theory then would be not the right tool for that. It would have to be a deeper tool that shows where evolutionary game theory comes from. My own take is that there's going to be a problem in doing that because space-time isn't fundamental. It's just a user interface. And that the distinction that we make between living and non-living is not a fundamental distinction. It's an artifact of the limits of our interface. Right? So this is a new wrinkle, and this is an important wrinkle. It's so nice to take space and time as fundamental, because if something looks like it's inanimate, it's inanimate, and we can just say it's not living. Now, it's much more complicated. Certain things are obviously living. I'm talking with you. I'm obviously interacting with something that's alive and conscious.
I think we've let go of the word obviously in this conversation. I think nothing is obvious.
Nothing's obvious. That's right. But when we get down to like an ant, it's obviously living, but I'll say it appears to be living. Yeah. But when we get down to a virus, now people wonder. And when we get down to protons, people say it's not living. And my attitude is, look, I have a user interface. The interface is there to hide certain aspects of reality, and others to it's an uneven representation, put it that way. Certain things just get completely hidden. Dark matter and dark energy are most of the energy and matter that's out there. Our interface just plain flat out hides them. Mm-hmm. The only way we get some hint is because gravitational things are going wrong within our. So most things are outside of our interface. The distinction between living and non-living is not fundamental. It's an artifact of our interface. If we really want to understand where evolution comes from, to answer the deep question you asked, I think the right way we're going to have to do that is to come up with a deeper theory than space-time, in which there may not be the notion of time, and show that whatever this dynamics of that deeper theory is. And by the way, I'll talk about how you could have dynamics without time, but the dynamics of this deeper theory, when we project it into in certain ways, then we do get space-time, and we get what appears to be evolution by natural selection. So I would love to see evolution by natural selection, nature red in tooth and claw, people fighting and animals fighting for resources and the whole bit, come out of a deeper theory in which perhaps it's all cooperation. There's no limited resources and so forth. But as a result of projection, you get space and time. And as a result of projection, you get nature red in tooth and claw, the appearance of it. But it's all an artifact of the interface.
I like this idea that the line between living and non-living is very important, because that's a thing that would emerge before you have evolution. The idea of death. So that seems to be an important component of natural selection. If that emerged, because that's also, asking the question, I guess, that I ask, where do fitness functions come from? That's like asking the old meaning of life question, right? Is what's the why? Why? And one of the big underlying whys, okay, you can start with evolution on Earth, but without life and death, without the line between the living and the dead, you don't have evolution. So what if underneath it, there's no such thing as the living and the dead? There's no, like this concept of an organism, period. There's a living organism that's defined by a volume in space-time that somehow interacts, that over time maintains its integrity somehow. It has some kind of history. It has a wall of some kind. The outside world, the environment, and then inside there's an organism. Mm-hmm. So you're defining an organism, and also you're defining that organism by the fact that it can move, and it can come alive, which you kind of think of as moving, combined with the fact that it's keeping itself separate from the environment. So you can point out that thing is living, and then it can also die. That seems to be all very powerful components of space-time that enable you to have something like natural selection and evolution.
Well, and there's a lot of interesting work, some of it by collaborators of Carl Friston and others, where they have Bayes net kind of stuff that they build on, and the notion of a Markov blanket. So you have some states within this network that are inside the blanket, then you have the blanket, and then the states outside the blanket. And the states inside this Markov blanket are conditionally independent of the states outside the blanket conditioned on the blanket. And what they're looking at is that the dynamics inside of the states inside the Markov blanket seem to be trying to estimate properties of the outside and react to them in a way. So it seems like you're doing probabilistic inferences in ways that might be able to keep you alive. So there's interesting work going on in that direction. But what I'm saying is something slightly different, and that is, like when I look at you, all I see is skin, hair, and eyes, right? That's all I see. Mm-hmm. But I know that there's a deeper reality. I believe that there's a much deeper reality. There's the whole world of your experiences, your thoughts, your hopes, your dreams. In some sense, the face that I see is just a symbol that I create, right? And as soon as I look away, I delete that symbol. But I don't delete you. I don't delete the conscious experience, the whole world of your. So I'm only deleting an interface symbol. But that interface symbol is a portal, so to speak. Not a perfect portal, but a genuine portal into your beliefs, into your conscious experiences, that's why we can have a conversation. We genuinely, your consciousness is genuinely affecting mine, and mine is genuinely affecting yours through these icons, which I create on the fly. I create your face when I look, I delete it. I don't create your consciousness. That's there all the time. But I do. So now when I look at a cat, I'm creating something that I still call living, and I still think is conscious. When I look at an ant, I create something that I still would call living, but maybe not conscious. When I look at something I call a virus, now I'm not even sure I would call it living. And when I look at a proton, I would say I don't even think it's not alive at all. It could be that I'm nevertheless interacting with something that's just as conscious as you. I'm not saying the proton is conscious. The face that I'm creating when I look at you, that face is not conscious. That face is a data structure in me. That face it's an experience. It's not an experiencer. Similarly, a proton is something that I create, when I look or do a collision in the Large Hadron Collider or something like that. But what is behind the entity in space-time? So I've got this space-time interface, and I've just got this entity that I call a proton. What is the reality behind it? Well, the physicists are finding these big structures, amplitude-hedron, the associahedron. What's behind those? Could be consciousness, what I'm playing with. In which case, when I'm interacting with a proton, I could be interacting with consciousness. Again, to be very clear, because it's easy to misunderstand, I'm not saying a proton is conscious. Just like I'm not saying your face is conscious. Your face is a symbol I create and then delete as I look. And so your face is not conscious, but I know that that face in my interface, the Lex Fridman face that I create, is an interface symbol that's a genuine portal into your consciousness. The portal is less clear for a cat, even less clear for an ant. And by the time we get down to a proton, the portal is not clear at all. But that doesn't mean I'm not interacting with consciousness. It just means my interface gave up. And there's some deeper reality that we have to go after. So your question really forces out a big part of this whole approach that I'm talking about.
So it's this portal and consciousness. I wonder why you can't. Your portal is not as good to a cat, to the cat's consciousness, than it is to a human. Does it have to do with the fact that you're human, and just similar organisms of similar complexity are able to create portals better to each other? Or is it just as you get more and more complex, you get better and better portals?
Well, let me answer one aspect of it that I'm more confident about, and then I'll speculate on that. Why is it that the portal is so bad with protons? Well, and elementary particles more generally, so quarks, leptons, and gluons, and so forth. Well, the reason for that is because those are just symmetries of space-time. More technically, they're irreducible representations of the Poincare group of space-time. So they're just literally representations of the data structure of space-time that we're using. So that's why they're not very much insightful. They're just almost entirely tied to the data structure itself. There's not much. They're telling you only something about the data structure, not behind the data structure. It's only when we get to higher levels that we're starting to, in some sense, build portals to what's behind space-time.
Sure. Yeah. So there's more and more complexity built on top of the interface of space-time with the cat.
So you can actually build a portal, right?
Yeah, right. This interface of face and hair and so on, skin. There's some syncing going on between humans, though, where we sync. Like you're getting a pretty good representation of the ideas in my head, and starting to get a foggy view of my memories in my head. Even though, this is the first time we're talking, you start to project your own memories. You start to solve like a giant hierarchy of puzzles about a human. Because we're all, there's a lot of similarities, a lot of it rhymes. So you start to make a lot of inferences and you build up this model of a person. You have a pretty sophisticated model of what's going on underneath. Again, I wonder if it's possible to construct these models about each other and nevertheless be very distant from an underlying reality.
Yes, there's a lot of work on this. So there's some interesting work called signaling games where they look at how people can coordinate and come to communicate. There's some interesting work that was done by some colleagues and friends of mine, Louis Narens, Natalia Komarova, and Kimberly Jameson, where they were looking at evolving color words. So you have a circle of colors, this is the color circle, and they wanted to see if they could get people to cooperate on how they carved the color circle up into units of words. And so they had a game theoretic kind of thing that they'd had people do. And what they found was that when they included, most people are trichromats. You have 3 kinds of cone photoreceptors, but there are a lot of men, 7% of men are dichromats. They might be missing the red cone photoreceptor. They found that the dichromats had an outsized influence on the final ways that the whole space of colors was carved up and labels attached. Mm-hmm. You needed to be able to include the dichromats in the conversation, and so they had a bigger influence on how you made the boundaries of the language. And I thought that was a really interesting kind of insight that there's going to be, again, a game, perhaps a game where evolutionary or genetic algorithm kind of thing that goes on in terms of learning to communicate in ways that are useful. And so, yeah, you can use game theory to actually explore that, or signaling games. There's a lot of brilliant work on that. I'm not doing it, but there's work out there.